In this video, I want to show you an application of Fourier transformation for multiplying polynomials. In this example, we multiply two polynomials. The first one is x squared plus x plus 1, and the second one is x minus 1. So we multiply x squared times x equals x to the power of 3. X times x is x squared. 1 times x is x. X squared times minus 1 is minus x squared. X times minus 1 is minus x. And 1 times minus 1 is minus 1. And finally, we add all the components together and we obtain x to the power of 3 minus 1. So when multiplying two polynomials, we have to multiply every coefficient of the first polynomial with every coefficient of the second polynomials. So in the worst case, when all coefficients are non-zero, we have n plus 1 times m plus 1 multiplications, where n is the degree of the first polynomial and m is the degree of the second polynomial. But we can do better if we apply Fourier transformation. We have two polynomials, p and q, and suppose that we can apply f4, the Fourier transformation matrix of degree 4. So we get 4 supporting points of the first polynomials, p1, pi, p minus 1, and p minus I, and 4 supporting points for the second polynomial. Then we multiply the corresponding supporting points, p1 times q1, pi times qi, and so on. And then this gives us the supporting points of the resulting polynomials, p times q. Then we transform it back with using the inverse Fourier transformation and obtain the polynomial p times q. Here I show you an example. We multiply the polynomials x squared plus x plus 1 and the second polynomial x minus 1. So the resulting polynomial has degree 3. So we have to use the Fourier matrix F4 using the fourth roots of unity, which are 1, I, minus 1, and minus I. So we write down the matrix F4. This matrix F4 consists of the fourth roots of unity. Now we write down the vector corresponding to the first polynomial, x squared plus x plus 1. Remember that we start from the lowest term, which is 1, then 1 for the x, then 1 for the x squared, and 0 for the x to the power of 3. So that's the first polynomial. And the second polynomial, x minus 1, the first coefficient is minus 1. So then the 1 for the x and the 0 for x squared and the 0 for x to the power of 3. So when we multiply now the first polynomial with the matrix, we have 1 plus 1 plus 1 equals 3. Now in the second row we have 1 plus I plus minus 1. 1 minus 1 is 0, so we get I. In the third row, we get 1 plus minus 1 plus 1, which is 1. And in the last row, we get 1 minus I minus 1, which is minus I. So for the second polynomial, minus 1 and the rest is 0, we have minus 1 plus 1 is 0. Then we have minus 1 plus I is minus 1 plus I. Then we have minus 1 plus minus 1 is minus 2, and the last one is minus 1 minus I. So those are the supporting points. The first column is supporting points of the first polynomial, and the second column is the supporting points for the second polynomial. Those are multiplied. 3 times 0 is 0, I times minus 1 plus I times I is minus 1, and I times minus 1 is minus I. Here we have 1 times minus 2 is minus 2, and here we have minus I times minus I is plus I squared is minus 1, and minus 1 times minus I is plus I. So those are the supporting points of the resulting, the product polynomial. And if we transform back into using the inverse Fourier matrix, you can do it at home. Then we get the following points: -1, 0, 0, 1, and -1 is the lowest coefficient and 1 is the highest coefficient. So this corresponds to the polynomial x to the power of 4 minus 1. So this is the result.